Give me 1 second.
Are you guys gonna send out the thing yet?
The worksheet? Sometime this week, for sure. Like actually. Do we need to make any more alterations, Dylan?
I already put that one important question. So I don't think so.
All right, so it'll go out by next session, for sure.
Or if not next session, before spring break. And if
Alright.
not, then.
The next day.
All right,
then-
I'm putting it in my to-do list right now. Send out Sam.
All
And
right,
the Kahoot, please.
Kahoot will do in class and then we'll send it out afterwards.
Yeah.
Well, we're not gonna do it in class, we'll do it in our little time here with each other. All right, so. Question 44 is saying a system receives 425 joules of heat from its surroundings and delivers 425 joules of work to its surroundings. What is the change in internal energy of the system in joules? And the change in internal energy equation, delta E equals the heat done on or by the system plus the work done on or by the system. So I don't expect y'all to have gotten here yet.
Did you post a video assignment on it yet? Like,
You do.
I heard Davidson went over Thermochem like a week ago.
Okay, he did go over a little bit of it. Like a little bit of this, but not much.
Okay. So what we need to think about is what is the system in terms of Q. We always denote that if our system is being heated up, then heat is being added to the system and we denote that with the positive sign, okay? So in this case, our system is receiving 425 joules of heat. That means our system is heating up, right? So our heat should be positive, a positive value, not a negative value. So Q in this case is positive. All right. So Q equals plus 425. And then the system also delivers 425 joules of work to its surroundings. So when we think about delivering work to our surroundings, we should think of the best analogy I can give is blowing up a balloon, okay? Well, the balloon is doing work on the surrounding air by pushing it out, because as we put air in the balloon, it's expanding in size, right? So it's actually pushing on the air in the room in order to get bigger, and it's doing work on the surroundings. Whereas when you have a balloon and you squeeze it and put I guess a lot of force on the balloon, you make the balloon smaller, and in doing so, you're doing work on the balloon. Okay, so if our system is delivering work to the surroundings, do we think that should be positive or negative? If our system is doing the work, think about you running a mile. You're doing the work. Are you gonna have, yeah, so it should be negative. And you can think of it, if you're running on the track, you're gonna have less energy after you ran the mile than you did before, right? So you lost energy, you did work to run that mile, you did work on the surroundings. So it would be negative, right? So W work is equal to negative 425. So our change in internal energy is equal to 425 minus 425. So our change in internal energy is just 0. This is a very easy intro topic to thermochemistry, and they only get a little bit more difficult, okay? And in this case, this one's really easy because both numbers are the same. The hardest part about this problem is assigning the positive and negative, okay? All right. So with that, try to do number 45. I'll give you maybe 2 minutes to think about it. And the biggest thing again is assigning your positive and negative, okay? So I'll give you the equation, delta E equals Q plus W.
You should give them the conversion factor.
Yeah, so 1 calorie is equal to 4.184 joules. All right. This one involves a little bit more math, unit conversions, but that's nothing that we haven't seen before. You can take this one, Rich. I'm gonna be walking around, so if you have a question that you don't want to ask the rest of the class, or you don't want the rest of the class, other 4 people to hear. Okay. Yeah. I'm making this a chapter 20.
Give me one.
Give me one.
Chapter 20.
About 1 minute. And if you don't know how to go about the problem, at least try to assign the signs that should be given to each value of work and heat. Thermal energy in this case is heat. All right, then time for people in class who were y'all able to get at least assigning positive and negative? Yeah. Okay. Good. Now we should go ahead and do it. Yeah, that's possible.
Okay, so number 45, what is the change in internal energy in joules system that releases 675 joules of thermal energy to its surroundings and has 530 calories of work done? So 675 joules, right? And it releases it. So what are we thinking for Q, positive or negative? Negative, right? So your Q would be negative 675 joules since it's releasing that heat. Now for our work, it has 500 calories of work done on it. So positive or negative? Positive. It is indeed positive. So I saw a bit of a confused face for that one. So imagine this, right? Say for example, like let's use Dylan's old analogy of like running a mile. Say for example, like you're really tired after running this mile, and then somebody like pushes you across the finish line. So they're doing work to you. So if they push you across, that means that the energy they gave you is like, you don't have to use any of your own energy. You're using the energy they gave you to cross the finish line. So that work is positive. Like that work is being done on you. Generally, right? We think of stuff that's positive, that's work going into something. And then if it's like negative, then it's being like released, going out. So going in is positive, going out is negative. So 530 calories of work done on it. We unfortunately have to do some conversions. So 530 calories. And then we know from the problem that 1 calorie is 4.184 joules. So if we solve this out, we'll get 2,217.52 joules. And this is being positive. So we'll plug it into our internal energy equation. So delta E equals our Q, which is negative 675, plus W, which is 2217.52. And if we solve that out, our delta E will be equal to a positive 1542.5 joules. And yes, the positive and negative signs do matter, because having work done on something is different than actually doing work. Like running a mile is different from like being like running, like having somebody like, okay, you actually running a mile is different from somebody pushing you in a shopping cart and them running a mile. That makes sense? All right. Any questions on that? On the test, will it be counted off if there's no positive sign? I mean, on the iClicker, it shouldn't be wrong if you don't enter a positive sign, because like 2 is the same thing as positive 2. But say if you entered like, say a negative instead of a positive, that's when it will be counted off.
Yeah, and when you have a negative delta E, you should put a negative sign in there. And also one other thing to note is that 1 calorie equals 4.184 joules is a conversion we need to memorize. So I don't know if you want us, I guess maybe we can highlight everything that is something you should memorize, okay? So we'll highlight in blue all the stuff that you should have known. And honestly, that's why I didn't put it in the problem, but I gave it to you because we're just starting chapter 6, so I don't expect you to know it just yet. All right, number 46, I can go ahead and do this. All right.
So find Q. This is going to be a very important equation down the line. This will be very, very important. Like in Gen Chem 2, this is like the first thing you learn or practice with.
All right, so find the heat when 22.0 grams of water is heated from 25 degrees Celsius to 100 degrees Celsius. So whenever you have a change in temperature for these types of problems, and how do we know that, how do we distinguish that this is different from a gas law problem? Because we also have change in temperatures for those types of problems as well. How do we know that this is referring to thermochemistry versus gases? It's asked for heat, right? So that's a good indication, as you should probably be thinking about something from chapter 6, all right? So whenever you're dealing with something from chapter 6 that talks about the change in or the heat associated with a change in temperature of a substance, in this case, water is our substance, and it's changing temperature from 25 to 100 degrees Celsius. We should be thinking about this equation here.
It also didn't specify it was a gas. That's another way you don't know that it's not a gas law problem. Like you'd have to be explicitly like, there'd have to be a gas specifically stated in the problem. And we all know that water is not a gas. So yeah.
So, and also, and also because it's asking for heat, and then chapter 5, we did not hear anything about heat, except for how heat can be applied to increase the kinetic energy of gas, but that's irrelevant here. All right, so it's asking for Q. It gives us the mass and the units. There's another thing that we need to know, and that is that the specific heat, C is specific heat. And what's the definition of specific heat, Rich?
It's the amount of heat required, or the amount of energy required to raise 1 gram of a substance by 1 degree Celsius.
Required to raise the temperature of a substance of 1 gram of substance by 1 degree Celsius. So I'm really lazy to raise temp of 1 gram substance by 1 degree Celsius.
And if you get confused on that, the units are pretty convenient.
Yeah, and so this is another thing that we need to know. I'm gonna highlight this area right here. That the specific heat of water is 4.184 joules per gram degrees Celsius.
Now, that's what I was talking about with the units, is the energies in joules, and then grams, grams, and then Celsius is your temperature. So joules per gram times degrees Celsius.
What does that say after 10?
1 gram, so 1 g of substance by 1 degree Celsius.
The specific heat can apply to like anything. There's like a specific heat of like water, aluminum, whatever.
Yeah. All right, so we have the mass, we're given mass, and how do we know that mass needs to stay in grams? Well, we look at our specific heat, and our specific heat in this case is in units of joules per gram degree Celsius, so grams is okay. Okay, so Q is equal to 22 grams times the specific heat of water, which is 4.184. And our change in temperature, our delta T is always our final temperature minus our initial temperature. So in this case, delta T is equal to 100 degrees Celsius minus 25 degrees Celsius, which is 75 degrees Celsius. So 75 degrees Celsius is our change in temperature, final minus initial. So if we did that correctly, you would put this into your handy dandy calculator. You should get a number of about 6,904 joules of heat. And this was, what would be assigned the value, or would it be a positive or negative number for the heat of the water? Positive, right? Because our water is being heated from 25 to 100 degrees Celsius. So it's gaining heat in order to do that. So we can put positive there. Alrighty, go ahead and try. I think it's a little too early. What do y'all say? Do you want me to give y'all time to try to work on this, or do you want me to just go through it? What? All right, so let's give y'all 2 minutes, try it, see where you can get, and if you can't get it, again, this is like probably the first stuff you've seen of thermochemistry. Don't worry if you can't get it right now, okay? If you can't get it in 2 weeks or 4 days, then you can start worrying, but right now, don't worry, okay? You got this one? And I do want to make one note, the Kelvin and the specific heat of aluminum is interchangeable with degrees Celsius. So you don't need to convert your units, your temperature to Kelvin, because at the end of the day, 1 degree increase in Kelvin is equal to 1 degree increase in Celsius. So 0 degrees Celsius in Kelvin is 273. 1 degree Celsius in Kelvin is 274. It's still 1 degree increase, right? So it's interchangeable.
For calorimetry today, is that a wise decision?
What?
The next 2 calorimetry.
We can do a review. Here and find some problems that we can go to, but not these go up. Gas related, so anything above. We haven't done that. You should do number 31. We're seeing if they're sure or not. I can deal with it, but yeah. Oh, okay. I mean, if We already did it, then we should give them time. Work it out. This one.
approximately 45 seconds and 32 milliseconds remaining. Thirty seconds. $15. And time, okay. So, number 47. If, or a 295 gram aluminum inch part at initial temperature of 13 degrees Celsius absorbs 75 kilojoules of heat. What is the final temperature of this part? And they're nice and they gave us the specific heat of aluminum. All right, so what equation do we use? It's up here. All right, so the people in the chemistry world call this Q equals MCAT. Q equals MC delta T. Because the triangle kind of looks like an A somewhat, I don't know, if you squint hard enough and use your imagination. So 295 gram sample, so we can go ahead and plug that in for a mass. Our specific heat is going to be 0.9 because it's the same thing Celsius as it is in Kelvin. Same difference, like if you have something in Celsius and something in Kelvin, same idea. And then we're looking for the final temperature. How do we find final temperature? There's a couple of different ways you can go about doing this. All right. Would you like the one-step way or the two-step way? All right, so the one-step way is that delta T, this is a delta, by the way. Anytime you see a delta, or let's highlight this. Anytime you see delta, that means change in something. And that'll be equal to a final temperature minus initial temperature. Change in anything is always final minus initial. So delta T, right? So if we know that delta T equals temperature final minus temperature initial, we can go ahead and plug in temperature final minus temperature initial. And we do have an initial temperature of 13 degrees Celsius. This is TF minus 13. And then we can go ahead and solve for this, and this equals 75 times 10 to the 3, because what we have to do is convert it into joules. So kilojoules, notice how our specific heat is in joules here. You have to convert this kilojoules to joules. So to do that, we'll just multiply by 1,000. So 75 kilojoules, and then 1 kilojoule is equal to 1,000 joules. So to solve that out, that's 75,000 joules. All right. Now we need to get our temperature final. So now it's just a matter of doing algebra to solve for our temperature final. So if you do 295 times 0.9, you'll get a certain number. Let's solve that out quick for algebra's sake. So if we do that, we get 295 times 0.9, which is equal to 265.5 TF. This is our temperature. And then we're gonna multiply this by 13. So that'll be minus 34515 equals 75,000. And then what you're gonna do, add this to 75,000. So we're gonna add our 3451.5 to both sides. 5. So 265 TF equals 78451.5. Divide both sides by our TF. So divide by 265 on both of our sides. And we will get a TF equal to 296.04 degrees Celsius. All right. Now that was a one-step way. Alternatively, what you could have done is solve for delta T. So make this into a delta T. So what you could have done is 295 times 0.9 again. So you get 265.5. And then from there, you could do 75,000 divided by 265.5. And you get a delta T of 282. And then from there, all you have to do is plug it in. So 282.49 equals temperature final minus 13. So if you add the 13 to both sides, you will get an approximate answer of, well, it's close enough here. So 295.49 Kelvin. We do it that way. Sorry, not Kelvin, Celsius. So you basically get around the same thing if you do the same answers.
So, well, what do we get from this? Besides that, Rich is a guy that likes numbers. So, I personally like variables. Variables make my life a lot easier. And it cleans up the entire mess that can be caused when you write 20 different numbers on your page, okay? So let's just imagine that I'm not erasing it, Rich, I'm just shrinking it. Okay? To a size that is a little different. Imagine you wanted to just work with variables, which is honestly what I would have done. And it makes the one-step way look a little bit nicer because you're not just plugging in numbers, rearranging numbers. So what our basic equation, our basic chemical equation that we're starting with is Q equals MC delta T. And like Rich said, our one-step way is to utilize the fact that delta T is equal to the final temperature, which is TF, minus the initial temperature, which we denote TI, and not the wrapper. And when you plug this into that equation, you get Q equals MC, and then TF minus TI. All right. So we know that we're looking for the final temperature. So now we use our algebra that we, I guess, learned back in high school, hopefully, to solve for TF. So we divide both sides by the MC. That crosses out there. And you should get this. So Q over MC is equal to T final minus T initial. So now the next thing is to add T initial to both sides. So you get Q over MC plus the initial temperature is equal to our T final. And I think once you see this equation, all it is the same thing Rich did, but now we're just plugging in all our numbers at one time rather than, quite frankly, doing all those and then left, like, I mean, it looks a little bit more chaotic. And it gave me anxiety watching that. And I can't imagine if this is the first time y'all are seeing thermochemistry, you must be like, oh my gosh, I'm about to, like, what the heck?
Some of y'all are engineering people, so the math part checks out for you, but if you wanna write out your variables, you can write out your variables.
Yes, so then we have our 75,000, so 75 times 10 to the third joules. Our sample size was 295 grams. And then our specific heat of the metal was 0.90. And then plus our initial temperature was 13 degrees Celsius. And however you put this into the calculator, as long as you do it correctly, you should get your answer of about 296 degrees Celsius, which is our TF. Or let me rearrange that so you can see what it. Oh, sorry. So our TF is equal to all that, which doing the math in the calculator gives us 296. All right. So again, if you're a math guy like Rish, I understand how messing with the numbers can be cool and all, but if you're trying to really just utilize your equation, manipulate the variables, and then plug in everything you have, which is what I do, and as you'll see later on the answer key, because I made the answer key, that's exactly what I do for each problem. I don't like working with the numbers. I feel like it's, I don't know. Yeah, I'm just gonna end it there. Anyways, any questions on that? Whichever way works best for you is the way you should do it. I think this one makes it a little bit nicer for people that are just seeing it the second, I guess the first time around. All right. So, let's go ahead and do number 48. I'll give you all 3 minutes to try to work on it and try to use the basic equations that we know. In this case, you're going to be using that Q equals MC delta T equation. So go for it, and we'll meet back up in 3 minutes. Start a timer for 3 minutes.
3 minutes. Counting down.
That's in glycol form. We got this for pizza.
Yes. By itself, not in the presence of acid. Creates an acetyl. That is not.
Acetyl or acetone?
Acetyl. Spelled ACETAL. All right, time is up. Looks like, raise your hand if you still need a little bit more time. Yeah, okay, so I'll give you all a little bit more time because I want you all to be able to try to at least get an answer. To your midterm undergrad. A plus. What does your exam raw score? Updated today at 5:27. What was it? 14.
If I show you the answer on my calculator, tell me if it's right.
Sure. And if it's wrong, you owe us, what kind of food do we want?
Goldfish?
For the sake of us getting food, that's wrong.
Is it right though?
Yeah,
Yeah,
okay. All right, I gave you all a little bit of extra time because I think it's really important that y'all try it by yourself before I go over it. And now I'll let y'all decide. Do you want the math, the almost math major to do it, or do you want me to do it with the variables? Okay, so we got some people saying variables, which I agree.
anybody like the math?
This guy, health careers guy. Oh, wait, what's? That's
2 votes for math,
What did y'all vote for? Variables? Okay,
2 for variables, 2 for math.
so variable? Okay, she wants variable. All right. What's the basic equation that we want to use for this problem? Q equals F cat, yeah. Q equals the one test that everyone's gonna have to take if you're pre-med. Okay. I know health careers boy over here. Doesn't have to take the MCAT. Another health careers kid. Alrighty, so. Again, for this one, it's asking us to find the final temperature, which is TF, right? T sub F. So delta T is equal to T final minus T initial. Plugging that in for delta T, we get Q equals MC TF minus TI. Solving for our TF, I did it in the previous problem. We did these steps here. We divided by MC and got there. So what we get after a couple algebraic things is that TF is equal to, let's see, TI plus QMC. Or wait, we're solving for, what is the initial temperature? I'm sorry, I was going in the wrong direction, guys. So TI is equal to, where is it? Okay. TF minus Q over MC. All right, and the way we did that again was we divided both sides by MC. So you got Q over MC is equal to TF. So I'll put that over. So you get something like this. And then you add TI to both sides, and then you subtract Q equals MC to both sides. On both sides, and you get TI is equal to TF minus Q over MC. All right. So from there, we can just plug in all of our information. Final temperature is 32.5 degrees Celsius. Our heat associated with this was 688 joules, But what is the sign for that heat? Is it positive or negative? Let's see, it says it's releasing 688 joules of heat. If the system, in this case, the ethylene glycol is our system. If our system is releasing heat, is that going to be negative or positive? If our system is losing energy. Perfect, negative. So negative 688 over our mass, which was 27.7. And then our specific heat of ethylene glycol was 2.42. All right. And the units are self-explanatory, joules per gram degree Celsius or per gram degree Kelvin, right? So plugging this into our wonderful non-graphic calculator for the exam, we should get a value of about 42.8 degrees Celsius. And as one of the people in our class did, congratulations. Again, it's just a lot of repetition with these problems. Once you do it enough times, it'll be like second nature. And as you see, using the manipulating your variables makes it a lot easier, right? Because you're not having to find one thing, find the other, plug in your numbers, rearrange. It's just simple algebra, solve for the variable you want, plug and chug, as we see here.
If I didn't do it that way, got the same answer. Like my way or that?
If you didn't do it, however you did it, and if you got the right answer, it's fine. Like you could have solved for delta T, and then you said delta T equal to final temperature minus initial, solve for initial. I don't know, how did you do it?
I just plug everything into the main equation. So there.
Oh, so this, like which equation, the one here,
Q equals MCAT,
this one or this one?
the first one.
So you solve for delta T.
Oh. So you did this. Oh, I did the first. Well, oh, I guess the second kind of.
Okay, so if you did this, that also works. That's basically the same thing as what I did. So is it a different one?
Well, like, I don't know. I didn't look at the same before.
I think it's like if you increase concentration of salt.
So you plugged all your numbers in and then solved, which is the same thing pretty much. I just solved for the variables first and then plugged in everything. Yeah. All right, so. Wait, the answer is 42.8 degrees Celsius, yeah. Make sure you use your negative sign here. You have a negative sign here and a negative sign here, which cancel out to give you positive number. That way you got Sydney, or was there an error on our part? All right, well, it's already 5:53 and the rest of the problems are a little too complex. I'll give you a second to look at it if you want. They're too complex for introductory to thermochemistry, so I wouldn't want to frighten anyone from coming to our sessions because we love our people that attend and we want more people. Sydney said I got 22.2, but it was probably an error on my part. So that's a difference of 10. So you probably switched up a negative somewhere because 32, you probably subtracted 10 instead of adding 10. And it also makes sense because if the initial temperature was 22 and the final temperature was 32, that means the system actually gained energy, but it tells us that it lost energy, yeah. So it makes sense that if the initial temperature was 42, because then that one should suggest that going from 42 to 32 is losing energy, right? For everyone here. But yeah, so we're done today. Have a good rest of your time here on Earth, and I'll see y'all